Welcome to the Tool Belt. I'm Anna Townsend, Managing Editor of Plant Services and your host for today's podcast. We're talking with Keith Riley, Product Marketing Manager for Level+Pressure at Endress+Hauser, which provides measurement instrumentation, services, and solutions for industrial process engineering. Today, I'm talking with Keith about asset health monitoring. What is it, how it impacts safety and productivity on the factory floor, and what's next for smart instruments. Hi, Keith. Thanks for joining us today.
Hello, Anna. My pleasure. Thank you for inviting me.
You bet. Well, let's get to it. We're talking today about asset health monitoring. So let's start off sort of at the basics. From an instrument perspective, what is asset health monitoring?
Well, Anna, you used the right term, basics. For Endress+Hauser, we look at it as the ability to identify the overall health and functionality of a smart instrument.
Okay. I'm sure it's really important in terms of how this affects the end user. So why is asset health monitoring so important to your customers?
It really extends beyond the instrument. Obviously, that's the first thing that you look at, but ultimately it's going to impact the safety and productivity of the facility as a whole.
Okay. And in what ways? Can you talk more about how asset health monitoring is impacting safety and productivity?
Absolutely. In certain situations, the traditional practice of run to failure can still be utilized. However, more often than not, we're seeing unscheduled downtime and maintenance as not being tolerated in a facility. It leads to increased maintenance expense and reduced productivity. That means predictive maintenance as an extension of asset health monitoring is really a significant benefit to the facility. Risk mitigation also comes into play, Anna. We already have numerous examples of the impact instrument failure can have on applications such as overfill prevention. Being able to dependably monitor the health of a device and identify issues prior to a safety event can significantly reduce the risks to both personnel and the facility. Finally, there's also the impact on yield. If your instrument is out of specification, what impact does that have on your throughput and the product quality?
Okay. So how are today's smart instruments tackling some of these issues?
First, we're using improved diagnostics to prevent faster and more accurate troubleshooting.
Okay. Can you give an example of what you mean there?
Absolutely. One of the best examples is the use of Nemour NE107 diagnostics in real-world situations. Let me give you an example. It's very typical that as a maintenance technician is out in the facility, he might see a warning on an instrument. And all smart instruments are going to give you this warning number, call it a W601 as an example, which is great because it tells you there is an issue and it is trying to identify what that problem is. But at this point, there's no way the technician is going to understand what that error code is actually trying to tell him. And this is the steps that typically happen. First, he's either going to call back to a control room for somebody to try to find the right maintenance manual for that instrument, or he's going to go back to the maintenance shop himself to try to find it, find the code, find the description of what it means, and then look at what the solution is. Nemour NE107 cuts through all that in several different ways. First, you're going to have a dashboard symbol on there that makes it very easy to tell the significance of what's going on. Is it a simple maintenance issue where the instrument is still giving out a valid reading, or is it something more severe? Right away, this helps them to start to prioritize how they're going to have to deal with it. Secondly, not only are you getting that error code, you're also getting a plain English description of the problem so that right away they have a basic understanding of what's going on at that point in time. Now, this is the really neat part. With a display and push buttons, you can actually drill down right there on the instrument and get an explanation of what the solution is to that problem, Or if you're using something like a Bluetooth communication and a smart app in conjunction with that, you can do the same thing. And within 5 minutes of being in front of the instrument, you can identify the problem, troubleshoot it, and know what your proper solution is versus spending 30, 45 minutes trying to track everything down.
Okay. So are diagnostics the only benefit available from these type of smart instruments?
Absolutely not. There's other benefits such as in situ verification. That allows you to perform a qualitative analysis on the instrument's overall health with a high total test coverage and also without process interruption. In other words, while you're performing that verification, the instrument is still giving valid process data to the control system.
Keith, can you talk about any specific use cases for this type of monitoring?
There are a number. One of the most common that comes to mind, Anna, is foam detection. The development of foam in a process is a common problem and one that can create a lot of expense. In most cases, the facility has no good way to know exactly when foam starts to develop, so they simply apply foam retardant on a very time-based schedule, honestly, regardless of whether the foam exists or not. As you can imagine, this can become quite expensive because foam retardant isn't cheap. Utilizing a radar device that can detect a reduction in signal strength as an indication of foam allows the control system to dispense the foam retardant on demand versus on a set schedule. This leads to a significant cost savings for the facility. Second example would be loop diagnostics. Pressure transmitters with loop diagnostics can identify issues such as corrosion or faulty wiring or power supplies that are starting to fail that otherwise would impact the quality of the 4 to 20 milliamp signal being received.
Interesting. Well, let's look into the future a little bit, maybe. And what do you see as sort of the next evolution in asset health monitoring?
Really, it should be creating easier access to the valuable process information already available in your smart instruments. Adopting technology changes such as industrial Ethernet protocols for two-wire instruments and advanced physical layer, commonly referred to as APL architecture.
Okay, so those are some really important technology changes going on right now. Can you talk a little bit more about how industrial Ethernet protocols and APL will improve asset health monitoring?
Sure, first it's going to make it easier and faster to access instrument data for analysis. Industrial Ethernet protocols have initial speeds of 10 megabytes per second versus the 1.2 kilobyte per second for HART. Plus, you're not going to be limited to only a 4 to 20 milliamp signal or a small number of visible parameters. Industrial Ethernet will also make it easier to separate control data from health or maintenance data. Control data can continue to be sent to the DCS or primary control system while the balance is regulated to a separate physical system or the cloud for easier access. This also limits the number of people that are actually in the primary control system. Ultimately, this will bring greater efficiency for the end user.
Great. Well, Keith, thank you so much for your comments today and your really great sort of real life in the field examples. I think asset health monitoring affects so many different facets of the business: safety, production, risk management, diagnostics. I could probably go on. So you've really given our listeners, I think, a lot to think about today. So thanks again for your time and your insights.
Thank you, Anna. It was my pleasure.